Hello, this is William from Visual Components. In this video, I'm going to show you how to model a product stacker, which is a type of component that can receive and stack components during a simulation. Now this video will consist of two parts. In the first part of the video, I'll show you how to model the component, and in the second part of the video, I'll show you how to control the component using a PLC. So welcome to the first part of the video. In this part, I'll show you how to model a component using a template, transform and edit geometry using expressions and parameters, create and set up a servo controller, assign a degree of freedom to a node and make that node interactive, and use Python to place components in different containers and in bundles during a simulation. So what you can see running in the 3D world right now is what we're going to create in part 1 of the video. So there's a basic feeder over here that's creating and feeding parts to the component we're going to model here, which is the product stacker. So there's a moving platform, and when the stack reaches a certain height, the platform moves up and ships out the stack. So in this case, the stack is 4 products. Alright, let's go and reset the simulation and get started. The first thing you want to do is open a new empty layout in the 3D world, which is what I've done here. I'm now going to add a component to the 3D world that I can model into a product stacker. In other words, I'm going to use a template. Templates are very helpful if you want to quickly create the components you need for a layout. For example, you can use any type of component available in the Visual Components Web eCatalog as a template for creating a new component, which is what I'm going to do right now. So I'll go to the eCat tab, and I'll be using the Web eCatalog 2014 source. In the search box, I'll find a component named Sensor Conveyor Template, which is this item right here. So I'll double click the item to add the component to the 3D World origin, click Fill to get a better view, and let's continue on to the next step. I can now edit the geometry of the component to resemble a product stacker. So I have the component selected here. I'll go to the Create tab. Notice the root node of the component is automatically selected and the geometry subtab is displayed. What I need to do is I need to modify the component to have a gap in between blocks so there can be a moving platform that moves up and down to stack products. So notice over here in the node feature tree there is a block feature, which you can see here, that has 2 operations assigned to it. So TGO, what this is doing is actually just aligning the block with the component's origin. So we don't need to adjust this. I'll close this out. The other operation, SGO, is actually scaling the geometry of the block along the X, Y, and Z axes using 3 parameters, which are conveyor width, conveyor length, and conveyor height. And parameters are used in this case to make the component parametric, so changing one value can update other parts of the component. Now what I can do is I can modify the length of the block. So here for scale X, conveyor length, instead of referencing the full value of the parameter, I'll go ahead and type here times 0.3 to reference only 30% of that value. So if I press the Enter key, you can see that the change I make is automatically updated to the block feature in the 3D world. So everything's looking good. Let's close this out. And what I can do now is create a clone or a copy of this block feature and move it over here next to this Out Frame feature. To do that, I'll go back to the Geometry subtab, Operation Features List, and I'll click Linear Clone. Now before I edit the properties of the linear clone, I'll close this out, and I'll go ahead and move this branch of features here into the linear clone. So I'll drag TGO into linear clone, and what this means is that when I make adjustments to the linear clone, I can see the changes it makes to the block feature automatically in the 3D world. So I'll double click linear clone to access its properties. And now for the count property, I want to have the original plus 1 copy, so I'll type here 2. And for the step or the distance between the original and the copies, we use 30% of conveyor length for the length of the block, so we can use the other 70% to be the distance between itself and the clone. So here for step, I'll type conveyor length times 0.7 and press the Enter key. And we can see the direction of the linear clone right here in this property is a vector, and the x-axis has 1 and the y and z have 0, so it's moving in this direction. And the distance here is space, so we have a nice gap here to create a moving platform. Let's close this out and move on to the next step. I can now create a platform in between these 2 block features and a servo controller to move the platform up and down to stack products. Now I only need to move part of the component, so I need to create a new node. I'll go here to the component node tree, right-click the root node, and then click New Link. So you can see here, link 1 has been added to the component as a child node, and I can now set up a servo controller. I'll select the root node, go to the behavior subtab here, and in this list here, I'll click servo controller to create the behavior, and notice the properties of the servo controller are automatically displayed for me. I'll click the joints button here to access the joints editor, and let's go ahead and create a new joint. So I'll click this button here, and let's rename the joint to be lift, so that's capital L-I-F-T, and let's change the type from rotary to linear, so I'll click this radio button, and let's close this out. Now in the flange node property of the servo controller, make sure it's link 1. It is, so let's close this out. And let's now set up the geometry for the platform. So I'll go to the component node tree, select link 1, and in the geometry subtab, let's create a block feature. Let's now edit the properties of the block feature. So let's give it a material of beige. And for length, width, and height, let's reference those 3 parameters of conveyor length, conveyor width, and conveyor height. So for length, we know that the blocks here are using 30% of conveyor length, so we can use the other 40% for the block's length. So conveyor length times 0.4, because this is 30% and the other block is 30%, so that's 60%, and we're using the other 40% here for the platform. Now for width, let's go and use the full value, so I'll type conveyor width, press the enter key. You can see things are happening here, I see you. And for height, let's use conveyor height, and we only need 10% of that, so times 0.1, press the enter key, close this out, and yep, there's our geometry. But we do need to transform this geometry so it's aligned with the edges of the blocks and flush with the top of the component. So in the geometry subtab, I'll go to the operations features list, click transform, I'll close this out, and then move block 2 into transform as a subfeature. I'll double click transform, and now I can write the expression and see the updates to the block. So I need to move the block along the x-axis using that conveyor length parameter, and I want it to be flush with this edge here. So I know that the block is using 30% of conveyor length. So in the expression, I'll type capital T as in translate, lowercase x for the x-axis, parentheses, conveyor length times 0.3. And if I press the enter key, yep, we can see the change is now aligned with that edge right here. So now we need to move the block along the y-axis in a negative direction, because let's close this out. You can see here in the floating origin, the positive direction of the y-axis is going that way. So we need to move it back this way so it's aligned with this edge here. And we can see that the block is also at half the width of that conveyor width parameter. So that'll be our reference. Let's double click transform and add to the expression. Go ahead and type a dot or a full stop or period, capital T lowercase y, parentheses, conveyor width times 0.5, because remember we only need half the width. And we need to move in a negative direction, so I'll add a minus sign before conveyor width. And if I press the enter key, yep, we can see now both of those edges are aligned. We now need to move the block up to the top edge here and align that. So I'll add a dot or period or full stop, uppercase T, lowercase z or z for the z-axis, parentheses, and for conveyor height, remember that the block here has 10% of that value, so we need to use the other 90% to move it up here. So conveyor height times 0.9, press the enter key, and yep, everything is aligned and good to go. Great. Let's now move on to the next step. I can now assign a degree of freedom and joint to the node that is being referenced as the platform, in this case link 1. So I'll go back to the component node tree, double-click link 1 to access its properties. You can see here it has a joint property. So I want the platform to move up and down along the z-axis. So for the joint, I'll write the expression capital T, lowercase z as in z, parentheses, and the joint for the servo controller that we set up is called lift, so I'll type L-I-F-T, press the enter key. There's no errors, so I'll close this out. And now to test the degree of freedom for this platform, let's go and create a jog behavior in the node. So I'll go here to the behavior subtab, and in this list here I'll click jog info to create the behavior. and its properties are displayed. So for DOF, or degree of freedom, let's set this to TZ. And for the variable, remember we're changing the joint called lift. So if I close this out, we have the interact button selected here. So if I hover over the platform, yep, I get the sign that it's interactive. And if I hold down the left mouse button, I can now drag that platform up and down. Ho ho, ho ho. But notice there are no constraints for the joint, so we should probably fix those. So let's reset the simulation to reset the joint. And let's assume that this joint here, this platform, is at its maximum value. So in order to set up a constraint, we need to have a minimum value that is probably right about down here, which would be the other 90% of the conveyor's height. So to set up that constraint for the joint, let's go to the component node tree, select the root node, and the behavior subtab here, let's double click servo controller to access its properties. Click the joints button here to access the joints editor. Click lift. And now for the max value, let's go and say that it's at 0. And for the minimum value, we can type conveyor height times 0.9, because remember the geometry of the platform is at 10% of that value. And we don't want this to go in the positive direction, so we'll add a minus sign here. So it's minus conveyor height times 0.9 for the minimum value and 0 for the max. So let's close this out. And we have the interact button selected here, so if we test this now, I try to move it up, but it won't move. So now if I move it down, yep, it stops right there flush with the floor. So up and down. Alright, let's reset the simulation just to make sure the joint is at its initial value and move on to the next step. I now need to use Python script to control the stacking of products. So in this platform here, I need to first set up a component container behavior for containing components, and then write some logic in a Python script. So in the component node tree, I'll select link 1, and behavior subtab here, I'll go and create a component container behavior. And I'll click close. We can just leave its default values. So now I'll go back to the root node, and you can see here this component already has a Python script behavior. So I'll double click it to access its editor, and let's go and move it over here to the side. And let's go and erase this while loop statement here. So if you're new to Python, I'll go kind of slow here just so we can go and understand everything. So at the start of the simulation, there are all these variables being defined. So comp equals get component. That's getting the component object that you can see here. The app is getting the application object, which is the 3D product. Signal is a behavior object. So in this case, it's the component signal, which is located right here at this sensor. So when a part arrives at the sensor, that signal will get the name of the component and it'll have a value of it. For path, that's the path behavior object, so it's the path that's moving the part. And we now need to set up some variables that can be the servo controller and the component container. So I'll type servo equals comp.findBehavior, parentheses, and we'll just use that servo controller, which is the name of the behavior that you can see over here in the behavior subtab. So I'm just getting that object, and then for a container equals comp.findBehavior component container. So this find behavior method is actually searching through all the nodes in the component to find a behavior that has this name. Okay. And now we need to write the loop for the program. So I'll use a while true. And then let's go ahead and create a list for the parts that we want to stack. So I'll type parts equals square brackets, which will be an empty list. So at the start of the loop, the list will be empty. And then I'll use a for loop. So for I in range, and this depends on how many parts you want in your stack. So let's do for colon, and now we have the indentation here. So in the for loop, what do we want to do first? Well, we want the path to be turned on, so I'll say path.enabled equals true. And I also want to make sure that the path, its capacity, is also available to true so it can receive more parts. So path.capacity available equals true. And then we want to use a condition. So in this case, we want to know when a part has arrived at this sensor here. And this sensor is actually connected to a signal that is already connected to the Python script. So you can see over here, there's a component signal, component path sensor. And if I double click component signal, you can see it already has one connection set up, which is the Python script. So the Python script behavior will automatically know the signal when its value is changed. So let's close this out. So right here, trigger condition. So this will wait for a trigger connected to the Python script to go into effect. Parentheses, and I'm going to use a lambda function here to return a true value. Lambda, colon, and I'm going to use a get trigger method. And this is helpful if you have many triggers in your component and you want to reference a specific one. So get trigger is equal to that signal object I have set up here. You can see. So if it's that component signal and the signal has a value, so in this case it won't return a true value if the signal has a none value or no value at all. So just to explain this again, the Lambda will test if the trigger is signal and the signal also has a value. And once that evaluates to true, the trigger will then move on to the next instruction. So let's now add a new instruction. So let's say, once we know the signal has a value, let's get the value of the signal. So I'll say part is equal to that component signal value. So signal.value. And I want to add that part to my parts list. So parts.append, parentheses, part. So that will get the part and add it to the parts list. So now to test this, we can go ahead and print this out. So I'll use a simple print statement. So print parts, and I'm going to use square brackets, and I'll just reference the range. So it'll either be 0, 1, 2, 3, and say parts, and let's get the name property of that object, a name, and let's also make sure it's saying part 1, part 2, part 3, part 4, not part 0, because at the start of the loop the I will actually be 0. So let's just add a +1, and let's go ahead and compile the code. And what I can do to test everything while I'm coding is add a basic feeder to the start of this component. So I'll go back to the ECAT tab, and let's go and do a search for a basic feeder. Yep, there it is. So I'll add that into 3D World and plug it into the beginning of the component here. So now if I run this simulation, I should get feedback in the message panel that prints the name of the component that is triggered at that sensor. So if I run this simulation, let's wait. Yep, so if I stop the simulation, you can see down here I actually get feedback. So everything is set up properly. Good. Let's reset this and continue writing the code. So I'll make this just a bit bigger and adjust the view. And now when I receive the part, I do want to stop the path. So actually we'll comment this print statement here by adding a hash. Let's do path.enabled equals false to turn it off. And let's also make the capacity available to be false. So path.capacity available equals false. And what we want to do is also grab the part to that node we set up in the component. In this case, that component container, which is this object right here. And what this means is that the part will be grabbed from the path and then contained in this component container behavior. So let's say container.grab, and this method will allow you to take that part from the path. It will grab this component that is equal to the part. And then we want to move the servo, so I'll type servo.move, and this method allows you to move all the joints in the servo controller. So we only have one, and we want to move that first joint, and the value we want to move it down is based on the part's height. So in this case we'll do I plus 1, and then we'll times it by 100, which is the height of the part. I already know that. So now let's go and compile the code and see how this works out. So if I run the simulation, I'll speed it up just a bit. Yep, the part actually moves up. Let's actually fix that. It seems I didn't add a negative sign there, so let's reset this and test this out. And this is also helpful for seeing how you can evaluate your errors in real time. So it's a good thing I added the basic feeder here, otherwise I would have been, whoa, it's moving up. So let's compile the code, and run again. So now the servo should actually move -100. And yep, there it goes. So another part arrives, goes again, and it keeps on going down. Alright, let's reset the simulation and keep on adding some instructions. So once I get all 4 parts, I'll go ahead and exit out of that loop, and let's now make the servo move back up. So servo.move 0, back to that 0 value, and I'll then go ahead and create a function that can compile or bundle all those parts in that stack. So go ahead and add a new function here. So I'll say define or def, and let's name the function pack bundle, and I'll take one argument that is parts, and let's now set up some instructions. So in this case, I'll say root of the stack is parts.pop. This will get the first item of the part, so the one that's at the bottom of the stack right there. And then we want to say for I part, or any other part in the parts list, we want to attach it to the root, so root.attach. And what do we want to attach to that root? We want to attach an I part. And then let's go ahead and say the root position is equal to well, we're actually getting a bit ahead of ourselves. So we'll first just attach all the components that are in that stack to the components at the bottom of the stack. And that's what we're doing here. We're saying that the root is the first item in the parts list, in this case the first component in the stack. And then for each other part in that list, we're going to attach it to that root. So if I compile the code and now add this bundle variable here, and then call that function I set up, so pack bundle, and I'm going to pass it the parts list that I set up here in this loop. And let's go ahead and add some space here between those guys. So let's compile the code again, run the simulation, and I'll speed it up just a bit. So we have 1 potato, 2 potato, and 3 parts, and after the 4th part is received, the servo should move back up. Yep, it moves back up. And I'll go and stop this simulation here. So what just happened? We can see in the 3D world that the first part in the stack is still visible, and if I select it and zoom out the view, we can see that the other 3 parts in the stack were attached to it, but they're at a different location. Whenever you attach a component to a different node, an offset is applied, and the components will reference a different coordinate system because they have a new parent. In this case, if I select the part here and turn on PNP, you can see that this blue arrow indicates that this part is attached to the first part, its parent. And this is the same for the other parts as well. Now the first part in the stack, I didn't attach it to anywhere else, so it's still attached to the node that contains the platform. Now if I select this component here, go to the Create tab, and double click link 1, you can see here in its properties that link 1 has an offset of 0, so it's still at the location of the component's origin, or its root node. So if I close this out and turn on translate, you can see here is the component's origin. So the offset from the origin to where part 1 is right now is being applied to these 3 parts in the stack. So to correct the position of these 3 parts, I need to take away that offset, and I'll show you how to do that now. So let's go and reset the simulation, and in our Python script for our pack bundle function, after we attach the part to the stack, let's then get the position of the root, or the first part in the stack. So root POS for position equals root.position matrix. Now, a position matrix is the position and orientation of a component, as well as some other stuff. But what you have to do first whenever you're editing or make an adjustment to a position matrix is get its value, or get the object itself. So after I have the position matrix, I'll then modify it. So I'll say root pos.invert to set it back to 0. And then we'll get the position matrix of the part. So I'll say ipart pos equals ipart dot position matrix, And then I'll create a new position from that. So new POS equals root POS, or root position, times I part POS, or I part position. So now that I have that new position, I now need to assign it back to the I part as its position matrix. So I'll say I part dot position matrix equals new POS. So you first need to get the position matrix, make the necessary adjustments, and then assign that value back to the position matrix in the part, or the component. So now that I have this, let's go ahead and compile the code. And to make sure we can see the changes in the 3D world while they're happening, let's create a delay here in the pack bundle function. So apologies for doing more work. Let's create a delay of 1 second. So compile the code, run the simulation. We should now see the changes happen in real time. So there's the first part. There's the first stack. And yep. So now when it goes back up, we'll see the magic. Yep, there's the magic. Boom. All right, so let's stop it right here. You can see now we have a nice stack of 4 parts. So now let's reset the simulation. And now after we make the part in our pack bundle function, we need to return the first part in the stack. And that will allow us to grab that stack into a different container, in this case the path. So in my pack bundle function, after we exit the for loop, let's go ahead and return root. So the other parts in the stack are attached to the bottom part, so we just need to return the root, and all the child components will be moved with it. So now in our while true loop here, we have the bundle, and now let's go ahead and take that path object and grab the bundle because it's returning the stack. Let me go ahead and change my typing there. And then after we have the path grab the bundle, let's turn the path back on. So path enabled equals true. And let's go and create a delay just so the while loop doesn't act kind of crazy. All right. So to quickly review, we created variables for our objects. We then created a loop during the simulation that will get the component that's at a sensor, add it to a parts list, and then attach all those parts to a bundle, and then move them along a path. So if I compile the code and run the simulation, we should see the stack formed first. So there it goes. Fourth part. All right, moment of truth. There it goes. And there goes the stack. Great. All right, so let's go ahead and minimize our Python script. And let's now add a conveyor to see everything happen in real time. So go back to the ECAT tab. Let's do a search for a conveyor. And there's quite a lot of conveyors, so actually we'll go to the Webby catalog, web catalog by type, and go to conveyors. Let's add a batcher conveyor. So now plug that in. Let's turn off the frames and see the end result of all this work. So we now have a nice stacker component. All right. And there's that delay again, and there goes the stack. All right. So let's go and reset the simulation and just make one last adjustment to this component here. So go back to the Create tab, access the Python script, and we don't need to see that delay of the parts being changed, their position being edited, I mean. So let's just comment out the delay and compile the code. So now what you can do is you can go ahead and select the component here. Make sure you have the root node selected, or you can just click the param tab to have the whole component selected. And then go on the File menu, go ahead and click Save Component, and then save the component as you would any other component. So you can give it its own name. You can say Product Stacker and change other information as well. So I'll click Cancel because I already have it saved on my device. And you can save this layout as well. So this concludes the video. If you want to learn more about how to model components, please feel free to visit our community at community.visualcomponents.net, and stay tuned for part 2 of this video to learn how to control the product stacker using a PLC. As always, have a great day.